Is there anybody in this in either of the sections who do not understand Bengali or have trouble understanding Bengali? If anybody, please speak out. I don't understand. Okay. So I'll mainly cover the course in English, but in case your friends may ask some questions, so I may revert to Bengali, but I'll try to cover up the entire session in English only. Okay. So just let me start the recording first. Just wait for the recording to start. Okay. Since this lab actually involves both the sections and also part-time students, so I'll record only one version and I'll distribute the link for this to both the part-time and UG students, right? And I'll cover both the labs, that is analog simulation, that is operational amplifier as computing elements, and study of transient response using linear system simulator. Now to start with, let us start with the experiment that is much more demanding, that requires much more explanation. That is the operational amplifiers as computing elements, right? I guess in your past courses you are quite acquainted with the operational amplifiers like adder, subtractor circuits, inverter circuits, integrator circuits, if I'm not wrong.
Yes, sir.
Right? But have you done any experiment in these circuits like adder, integrator circuit in your digital electronics class or analog electronics class? Sorry.
Yes, sir. Yes, we have done few.
Okay. So let us start with the analog simulation part. For that, we should start with the setup. Just a second. Someone is trying to enter. Okay. So this is a setup that we'll be using for using operational amplifiers as computing elements, right? So if you look closely at the setup, see what are there in there. At the top, there are these things which are called the, sorry, I should revert to red color. These are called pods, right? They're basically potential dividers or helical potential dividers. What does they do? You give an input signal, say a 10 volt plus 10 volt, and you get an output signal. And this input to output conversion takes place like this. There's a variable output part over here. So if you give a total 10 volt of input, and then by just moving this position of this potentiometer terminal, you can change the output voltage. This is a linear one, but in this port we have a spring that is connected in a helical manner, and there is a connector like this, which gives you the output terminal, right? So like this, what you can do, you can obtain different output voltages corresponding to given input voltage, and this will be used to set up the, also called the coefficient port. That is, you can set a variable gain using this port. Right? Now, before I start, why I'm talking about this port? Because this operational amplifiers will be used to solve first algebraic equations. What do you need for algebraic equation? Summer, subtractor, inverter, right? And in some cases, gain. So to obtain these gain values, normally how the gain is represented? This is a gain alpha. You give an input and you get an output. If you give xt as an input, then your output will be alpha xt. This alpha value is set using these ports. Okay, so these ports can be used to simulate a algebraic equation, right? Further, you can also solve what is called a differential equation. So this will require a summer, subtractor, inverter, gain. Additionally, what would be needed is an integrator, right? Because we know a differential equation requires integration to give the results. But to start with, we will only consider algebraic equation, and for that, we should be having a summer. Subtractor can be improvised from the summer by making one of the inputs to the summer inverting through the inverter. So this summer and inverter can be used to obtain the subtractor. So there is nothing new in a subtractor, and gain will be there to provide enough weightage to the signal, right? So let us see how these components are there in the circuit. So we have already seen the gain elements, that is a port. So you can set different gain values depending upon your equation or the linear equation that you are dealing with. Then in the next row, we have this. These are all, sorry, summer come inverter, right? So because in your algebraic manipulation, what you need is basically a summation. If you put a signal, if you want to have x minus y, what you can do? You can input x and minus y. How this minus y can be obtained? By inverting y. So a summer will do. See, in this summer, there are 1, 2, 3 inputs which are indicated by gain 1. I don't think I need to explain about this the summer circuit or realization of summer circuit. It's very trivial. I think you have all done that, right? So what is important is that there are 3 terminals marked 1. So whatever input you give here, that will be multiplied by gain 1. But there are 2 terminals that are marked by 10. Because whatever input you give here will be multiplied by a factor of 10. Right? Now, why this 10 is required at all, that I will discuss. Another very, very important thing that is to be mentioned here is this summer is basically a multi-input inverter. That is, if you put A and B to its input, the output will be minus of A plus B. So it is basically an inverting summer. If you put only A, the output will be minus A. So it is basically an inverter or a summer with an inverting gain, right? So this is how you can use a summer as a summer or inverter. Suppose you want to have a subtraction of 2 signals. What you can do? You can put one signal over here directly and put another signal over here, take the output and put it back here. So it will be, if this is A, this is B, the signal will be A minus B. So by this way, you can obviously simulate a subtractor using this summation block, right? So this is the second part, the summation, inversion or subtraction that can be carried out using this. So this will help you in deciding or solving the algebraic equations. And for the sake of time management, I have not included this portion in my experiment because this is very trivial. Just summing two signals and getting the result. And but one thing is to be noted here that these are not ideal summer or ideal inverter. Right? That can be seen if you look at the result. I have a result for you. See the connection diagram, how the connection has been done. If I zoom in, sorry, I've zoomed it too much. This plus 10-volt supply, this is a plus 10-volt supply, is connected to this one input terminal, right? So what do you expect at the output terminal? The output terminal should have a value minus 10 volt ideally, since it's a simple inverter. So what we are doing, we're just connecting the output terminal to a meter that is provided over here. So you see, due to some supply problem, the input was like 11.90 volt. So we expect the output to be minus 11.90 volt, but due to, since it is not an ideal inverter of having unity gain, it has some gain, so the output will be 10.06 volt. Okay, but it is inverted, and it's just because it is connected in such a way, it's not showing a minus sign, but it's inverted. Okay, I've just put it this way so that it's showing plus 10, but the connection is reversed actually. This plus minus are reversed. Okay, anyway, so this important thing is to note that this gain is never 1. So you'll get some attenuation to the inverter or the summer or the subtractor, whatever you use. Your output will not be simple A plus B, it will be alpha into A plus B. The alpha will be the attenuation factor of that particular summer. Or alpha into A minus B, that will be the attenuation factor of that particular summer. Right? So this is the first part of an experiment that you have to study the summer inverter and see how the gains are changing. Actually, it's working with the summer or not. So I've skipped that part. So what is more important is the solution of differential equation or integral differential equation. Right? So let us consider a simple example. Okay, and then I think that will be much easier to follow rather than going for this elaborate discussion. Say we have a differential equation given like this. So this only will not suffice. We have to also mention the initial conditions of x0. So this is 0 and x dot 0. Say this is equal to 1. So we are required to solve this differential equation using the operational amplifier circuit, or that is called the analog simulation. This is called the analog simulation. I should mention the term. Why it is called an analog simulation? Because we are using analog integration, which is based on op amp or analog circuit. So the procedure for solving this analog simulation will be taught in your class in much more detailed manner. So just for the sake of understanding of the lab, I'll just go through the key points. So the main idea behind this analog simulation is that since you're dealing with real-time signals or analog signals, the main objective is to find out the value of x double dot t. Because if you have x double dot t, then you integrate it once, what you will get x dot t. Then you integrate x dot t again, so you will get xt. So effectively, your first objective will be to obtain the expression, obtain a value of x double dot t, and feed this value to an integrator. The output will be x dot t and feed that value to another integrator. So at the end of the second integrator, you'll get the value xt. So it will be, if I draw the block diagram, it will be something like this. And simplify block diagram. Right? So this is x double dot, this is x dot, and this is your x. So this is the theme behind this analog simulation. This is the motive or the objective. So how, let us see how this objective can be fulfilled. If you write down the equation, I can write down the equation in this manner: x double dot, sorry, t can be written as right. Just by putting the things in order. Then you find out the expression for x double dot t in terms of and summer. Suppose we have a summer, but you know it's inverting summer. If you want to have x double dot here, then what should be the input, different inputs? So to get this 4, we should apply a signal of value -4. To get this minus xt, we should apply a signal x over here. To get this minus 0.5 x dot t, we should apply a signal 0.5 x dot here. So at the end of the day, what you will get, your x double dot will follow this expression, right? So by this way, I do not know now. Still, I do not know how to obtain this x and 0.5 x dot. But I know if I obtain these values, I can get x double dot. So what I will do, I've already seen that if I put an integrator here, this is a symbol of integrator. Okay, mind it, it should be mentioned that this is a inverting gain integrator. So what you will get at the output? You get minus x dot, right? Then this all should be multiplied by 1. This 1. And then you get another integrator. What you'll get? You'll get x, right? Now you have information, real-time information on my x dot, this minus x dot and x. So I can now suitably feed these signals back. Okay, how this can be done? Suppose I want to feed back this x. This is x, this is x. And your equation, there is no coefficient. So what I can do, I can simply connect this. Follow? So I'm getting a signal x and I'm feeding it back to this first summer. What is the left? 0.5 x dot. So how this can be done? We have minus x dot, right? So multiply it by a gain of 0.5. So what do you have? Minus 0.5 x dot. Now put an inverter. So what do you get? You'll get 0.5 x dot. So this is an analog simulation diagram that will solve this second order differential equation. What you have to do? You have to only provide this input. Because if you see the previous page, the equation, this is the input, the external input. So you have to just provide this external input. So I guess everybody has understood this thing. If you have any doubt, please ask.
স্যার এখানে মাল্টিপ্লায়ার হিসেবে কি মানে অ্যাম্পলিফায়ার ইউজ করছি?
হ্যাঁ, ওই অ্যাম্পলিফায়ার ইউজ করছি, আমরা পটগুলো ইউজ করছি, যে পটগুলো দেখালাম।
ও আচ্ছা আচ্ছা,
this is basically a pot. Okay, then I will explain how this pot are used. And this is an inverter. Okay, see, the only thing is that in analog simulation, we are not bothered about the expression for x or x dot. What we are bothered about is the actual value of x and x dot. There's a real-time value of x and x dot. Both are analog signals, and they should be fed back to the summer so that they conform to the equation, differential equation. দেখো 0.5 x dot ছিল, so x dot কে আমি 0.5 দিয়ে মাল্টিপ্লাই করলাম, মাইনাস x dot কে ইনভার্ট করে দিলাম, so it is flipped back as 0.5, so that the x double dot in here, আমার মেইন উদ্দেশ্য হচ্ছে this x double dot should follow this equation, and that is absolutely fine. ঠিক আছে, এবার দেখো the only thing that is remaining is the initial condition for these two cases. So this is, you have to incorporate the initial condition for the variable x dot, but since this is a minus x dot, so you have to consider the initial condition of minus x dot 0, that has to be inputted here, and this one you have to consider the initial condition of x 0. So there is another catch here. Since this is an inverting amplifier and inverting integrator, this value should be fed with an inverter, that is with a negative sign. So for solution of x, you should not incorporate, or you should not input the initial value of x0, rather you should put the value minus of x0, so that the actual value of x0 after inversion appears at the output. We'll see that. We'll exactly see that in the next part. Okay, when we discuss about the components. So I'll first discuss the objective, then I'll individually build up the components. Any question? Bolo. Now, because all these chips that we have, all the inverters, all the summers, integrators that we have are normally, that are available, are inverting type. Okay, তোমরা দেখবে যে conventional integrator that you have studied, they're also inverting type. So that's why it's much more common. Among the setup that you're using actually in your laboratory, they're also built up based on this inverting type components. Okay, but for computer simulation, if you want to simulate this in your computer environment using, say, Simulink or PSpice, then you can use your general non-inverting integrator, non-inverting summer. There's no point, no problem. But since we are using only inverting integrators, inverting summers, we need to incorporate that in the theory as well. Okay, and that's a general practice because they are easily available and they are affordable, right? So, but in this circuit, there's a problem. See, we have okay. Before going to the next step, let me first introduce to the integrators. Then you consider. Then you see the corresponding terminals. Follow. একদম একদম আমি দেখাবো, এটা এক্সপেরিমেন্টাল সেটআপে দেখিয়ে দেবো, ঠিক আছে কি হচ্ছে, ঠিক আছে, কারণ যাই দেবে তুমি ইনভার্ট করবে। Coming back to the setup, I'll show you the integrator. So these are the integrator. I'll zoom in a bit. This is the integrator block. So it has already 3 components with 1 gain, and 2 of the input components are having gain 10. And there is this IC terminal. This is your initial condition terminal, right? So this integrator has already the summer incorporated in it, right? So you can use this integrator to integrate and as well as do the summation simultaneously, right? So what we are missing out in this particular graph or the particular realization of circuit diagram, this integration has 3 to 5 inputs with 3 multiplier 1, 3 inputs having multiplier 1 and the rest having multiplier 10. So you can have integration as well as summation. Okay, you can integrate 2-3 signals and the summation simultaneously. So what we can do, we can club this summer and this integrator together. So what is the advantage? See, in this case, how many connections are there? 1, 2, 3, 4. So these 4 connections from these 4 connections, we can reduce at least this one connection. And this will also reduce this extra component to the inverter. Since these are not ideal inverters, what will happen if you introduce the inverter? The gain of the inverter will take place. So x double dot will not be exactly x double dot, rather alpha x double dot. Just to eliminate that situation, what we will do? We will club these two together. So how the expression would now look like, or the realization would look like? What we will have? We'll have integrator 1. The second integrator will be as usual. Second integrator will be there. The output of the second integrator is x, and the first integrator is as usual minus x dot. I think someone is trying to enter. So this portion remains same. Now, if I want to add this signal to the input of the integrator, what I'm missing out? I'm missing out on this inversion. Again, another person is trying to admit, right? So I'm missing out on this inversion. So what I can do, I can simply add this is a gain 0.5. Do you agree with this? See, this signal was passing through an inverter, then going to the integrator. Now I've omitted the inverter. So there's no inverter. So this inverter has to be taken out so that this effect of this -1 gives you +1. So this will be putting right back to there. So to the integrated input, this signal will remain unchanged, right? What about this signal? This was going right through without an inverter, but after that it was going through an inversion to the integrator. So this one, remove the inversion. You have to put an inverter. Understood? And thirdly, this signal is -4 going to the inverter. So it was giving +4. That was coming over here. So we have to put a +4 directly. Now, how this +4 can be put? We have a 10-volt source. You put a pot sitting at 0.4. So what is the signal over here? 4 volt. Right? Now, initial condition. For this, x00 is 0. So you can simply ground this. There's no need to put any initial condition for the second integration. But for first integration, you have x dot 0. Sorry. 1. How that can be incorporated? So what you have to incorporate here? You have to incorporate minus x dot 0 because the integration yields minus x dot. But since there's an inversion, so I have to put so what will be this value? 1. So how that can be put? You just apply again 0.1 and apply plus 10 volt source here. So followed. Pardon for my drawing, but this will be the final simulation diagram that will yield you the result. This xt, if you can watch this xt over scope or any meter, this will give you the exact transition or time response of the solution of this state equation. Agreed? Let us see. The new things that we have understood here, that for that what we require different port settings. 0.4, 0.1, 0.5. let's begin with this port settings. Then we have to see how this integrator works. So first let us check how the port settings are done. Bolo. আচ্ছা এখানে you are solving for minus x dot. So what should you input তোমার ইনপুটটা কি হবে তাহলে minus x dot 0 দিতে হবে যেহেতু x dot 0 না তুমি minus x dot সলভ করছো তাহলে এখানে যদি minus x dot 0 তুমি পেতে চাও এই আউটপুটে তাহলে তোমাকে এখানে কি দিতে হবে মাইনাস অফ দ্যাট কারণ তুমি সলিউশন করছো মাইনাস x dot এর জন্য সুতরাং এখানে একটা মাইনাস এখানে একটা মাইনাস মাইনাস প্লাস হয়ে গেল তাহলে 1 হয়ে যাচ্ছে তুমি যদি সলভ করতে x এর জন্য তাহলে তুমি x0 দিতে তুমি সলভ করছো কার জন্য মাইনাস x এর জন্য তাহলে তোমাকে দিতে হবে মাইনাস x0 তাই তো ইনিশিয়াল কন্ডিশন আর মাইনাস x0 তুমি যদি আউটপুটে চাও তোমার যেহেতু এখানে একটা ইনভার্সন আছে তোমাকে তাহলে দিতে হবে মাইনাস অফ মাইনাস x0 তাহলে প্লাস x0 ঠিক আছে তাহলে এবার ফার্স্ট ওয়ে টু সি হাউ দিস port setting is carried out, right? So for that what we have in a setup, I guess I have some extra figures. Yes, so this is the port setting setup. What we have here is called a reference port. Why do we require this reference port? Because if you look at the previous figure, in these ports, if I zoom in, there is no calibration. What you can have to the extreme, this point, this is 0, and to the extreme right point, this is 1. In between, you do not have any calibration. So how can you set the value at 0.4, 0.1, 0.5? For that, we need a calibrating port, right? Port that will help you to calibrate. And that port is basically this reference port. Now, there is another mechanism that is over here, which enables you to view the value. There is a meter. There is a meter over here. Now, this meter is basically a dual mode meter. Now, why I'm calling this a dual mode? See, this is a toggle switch. One is meter volt. When you put this toggle switch in the meter volt position, there is an input to the meter. Whatever signal is coming over here, it will display that value over here using this needle. But if you put toggle the switch to this port set position, then what will happen? It will not show the value of this signal. So what it will show? It will show the reference value minus that value. That is, I'll explain. Suppose you want to set a value of 0.5. Now this reference port has calibration 0 to 1000. Right? To set 0.5, you have to set the reference port to 500. And this is like a simple 1 year scale like arrangement. If you put the reference port at 500, this reference port is already connected to a plus 10 volt input. So the output of the reference port, what will be the value? 5 volt, right? Since the port setting is 0.5, the reference port setting. So this 5 volt will appear across a terminal here, red terminal. So what I'm doing, I'm connecting I should omit these things, otherwise it's very difficult to see. The same 10 volt supply to say port number 1. Right? I'm connecting the output. The 10 volt supply I've connected to port 1, and I've connected the output of the port back to this meter. Right? Now, if I put the toggle switch to meter volt position and turn on, it will show you a value. That is the value of the value corresponding to the pot position. So output will be alpha input. So you can change the pot position and get variable alpha. But what we want to have is a fixed value of alpha. So what do we have to do? We have to toggle the switch to pot set. Under this condition, what it happens is actually is the output of this reference pot, which is already connected to a plus 10-volt supply, is coming over here, and that is nothing but your 5-volt. Now we have connected. Sorry, I think I should use another color. I think green is not visible. What about yellow? I have connected plus 10-volt to the variable pot and connected the output brought over here. So when the meter is in pot set condition, the meter will show you this differential voltage. So this differential voltage may be positive or negative. To indicate that, there are two lamps. If it is positive, the red lamp will glow, and this value will give you the positive expression. And if it is negative, then the green lamp will glow, and it will give you the negative impression. This needle is moving in only one direction, so this positive negative is indicated by this way. So now what you have to do, you have to change the pot setting until these two voltages become exactly equal. When they become equal, you will be assured that the pot is set to that 0.5 value. So this is how this pot is set at different values. ঠিক আছে? থিওরিটা বুঝতে পারলে? Have you understood the theory?
স্যার এখানে কি স্যার ওই যে মানে নবটা আর কি দেখাচ্ছেন ওখানে যে রেড কালার দিয়ে ওই নবটা ওটা ঘুরিয়ে ঘুরিয়ে কি মানে ওই প্লাস 5
না,
ভোল্ট বা
এটা তুমি
ওখানে
সেট
অন্য
করবে।
ভ্যালু
This is
সেট
for just
করছি?
for setting this value. You set this value to 500. So that will correspond to 0.5 gain. So this you not change that. This is a reference point because there is a calibration. Okay. What you have to do, you have to calibrate the individual pots with respect to this value. For that, this differential voltage will be expressed, and a point will come when this needle will be 0 and neither of the lamp will be glowing. That means a null position has been achieved, right?
Okay, sir.
So that the value of the pot, the variable pot, is exactly equal to that of the reference pot. I have a video for that. I will show you the video now. Okay, then everything will be clear. So this is a theory. Obviously, the practical is much more easier to understand, right? Just wait for a minute. See this connection? Now what I'm doing, I'm actually changing or rotating the pot. Okay, in a clockwise sense. Starting from 0, I'm rotating it. I'll show you the meter readings in the next video until a balance is reached. As soon as you reach the balance, I'll see it is set. See, I'm just rotating this pot. So what I'm seeing over here is in the next video. Let's check that. So this is when you started. This is the value. See, it's showing negative. Since the green lamp is glowing. So I have to have what I have to do. I have to increase the voltage by moving a pot in a clockwise sense. So the pot setting moves from 0 towards 1. So I will do that. Continue to do that. So I'm moving that. Still rotating in the clockwise sense. And this green lamp is still growing. Now it is decreasing. See, now suddenly it has become 0 and the red lamp is glowing. If we get back slightly, you see at this point neither of the lamp is glowing, right? And the deflection is minimum. That means the pot setting is exactly in unison or in agreement with the reference pot setting, so that their output voltages are same. How that can be ensured? I have to just see. I have to just change the pot setting or the toggle switch from pot set to meter volt. See, 5 volt I'm getting. So it has been set to 0.5. I'll repeat that. Slowly. Now it is starting to decrease, but they're coming close. At this point, see, there is slight loose contact. See, the pot position or the toggle switch is in pot set position. So it shows the differential voltage, right? Now, once we reach the null, what we will do? I'll simply move over to the meter volt position, and the value it shows 5 volt. What is the value of the pot set now? 0.5, right? So this is how you can set the pot at any given value. Understood? Okay. Now, once you have decided how to set the pot, now we should study the integrator circuit. Okay. How the integrator circuit behaves. Now, in the integrator circuit, what we have basically, if you look at the connection diagram, these are integrators. This is a key components of the integrator circuit. These 3 switches. One is called set. This will be used to set the initial condition. This is operate. This will cause the integration operation to start and continue. This hold will make the integration to pause at a particular value. Right. So for that, what we will do, we'll put a constant input of the integrator and see how the output behaves. So if you put a constant input, say 1 volt, and the integrator time constant is 1, then you'll get a ramp signal at the output, right? It will be continuously moving up. See how that can be seen. But you should also remember the fact that this is an inverting integrator, right? So first, what we will do, we'll put an initial condition. Instead of the previous video, let me switch over. See, the connection I've made, what I've done, I've connected a plus 5 volt to the IC terminal of the integrator. What is the IC terminal? We look at the setup. Right. So say we have taken this integrator, and to this integrator, I have connected 5 volt. So how do you obtain a 5 volt? Take plus 10 volt, pass it to the port that you have set at 0.5 and apply it here, right? So I have applied the 5 volts. So whenever I put the set button, what do you expect? You will expect the output of integrator to move to minus 5 volt, right? And then At the input, say I have provided an input 1.2 volt, right? So what will happen if I draw that diagram, timing diagram? T, this is YT, this is 0. Is it visible? I should draw in a board. T, this is YT. So at T equal to 0, as soon as you switch on the integrator, what will happen? You'll jump over to a value minus 5 volt. Then as soon as integration starts, you start integrate. What is the input value we have? 1.2 volt. So in which direction will the integrator go? Integrator output go in this direction or in this direction? Anybody? Blue line or the green line, which will be the same? Which will be the correct one?
So green line.
Exactly. Since it's an inverting integrator, right?
Yes, sir.
So let us see. Let us see what happens in the actual simulation. See, I have not yet set the value. Start from the beginning. As soon as I turn on the switch, I set it. It reaches the value 4.3. Just wait a minute. I should remove these things. Then I think I should restart it again. It's not yet started. Oh, sorry. I missed the point. Just a second. And this is the starting point. This is the starting point. The output of the integrator is 0. There's no input connected because this power is switched off. As soon as you start the power, the input is 1.2, and there is some stray capacitance. For that, there is an initial value of the integrator, but the initial condition is not, impression has not yet come. So just now I am putting the set, pressing the set button. This will set the initial condition to the integrator. See what happens. So we expect the output of the integrator to move to -5 or near about that value. It has reached that value, -4.83. So it will stay there because we have not put the operate button. So integrator is not operating. It is just getting an impression of the initial condition and showing the output. As soon as you put the operate button, it will start integrating. And as your friend have mentioned, it will grow in the negative side. See, if I press the hold button, it will hold on to this value. See, it holds on to the value. It will start counting once we put the operate button again. Now, how long will this integration take place? Since these are all op-amp circuits, they are excited or they are provided with a plus minus 15 volt bias. And we all know the op-amp output cannot exceed this bias voltage of plus minus 15 volt. So time will come when the output voltage will near about this 14.8, 14.9 or 15 volt. This will not grow because it is beyond the biasing voltage of the op-amps. So we'll get saturated. See, it got saturated at -14.3. But theoretically, it should integrate beyond that as well. What we're actually getting is that the graph up to this point it moves, then it saturates at -14.30. Right? So this is not a very favorable position because we're only getting an integration of this up to this period. So if you want to increase the integration period, what you have to do? You have to make the input 1.2 volt. Then it will start going from this direction. It will continue until say 14.3 in a positive direction. So the length or the duration of integration will be much more. Understood? I guess I have that result. Let me check. Let me check that result. The next video. Okay, see. No, this is not the video. Sorry. So this is the video where the input signal is now minus 1 point. Right? Initial condition is set. The set button is glowing. So it's minus 4.84. Now let us see how the integration operation takes place. As soon as we start again, set it, then it will operate. See, it is going in the positive direction. It's increasing the value. So this will continue for even a longer period of time. Unfortunately, it saturates at 13.57. Okay, so I've seen how this integrator actually operates, right? Now what we have to do, we have to simulate the equation that is given. But in our laboratory, we generally simulate a different equation, not that equation that I have discussed. I will discuss the equation now. The equation that we will be simulating in laboratory. And unfortunately, the equation that is given in your laboratory instruction sheet is not that I have simulated because of this pandemic situation. I could not get the opportunity to simulate that. What I have simulated is an equation like this. X double dot t plus 1.25 x dot t plus 1.96 xt is equal to something like this. Okay, not 1.96, it's 0.98, I guess. Yes. Sorry. This is 0.98. This is the equation that I have simulated. There's an interesting thing. First of all, this gain is 1.25. How do you simulate again 1.25? Because we have a pot whose gain can vary only between 0 to 1. Then how to set 1.21, 25 or 1.96? What you
স্যার
can
একটু
do?
ওয়ান আর একটু
We use
Follow?
two pots. মানে একটা ইনপুট নিয়ে আরেকটাকে ক্যাসকেডেড মানে আরেকটা আউটপুটের সাথে আরেকটা ইনপুট দুটো পটের ইনপুট কানেক্ট করে করলাম।
That is okay. That is okay. But why we use so many connections? Because already I've mentioned that in a setup you have these pots with multiplier 10. Right? So what you will do? You set up a value 0.125 and put that to the input where there is a multiplier 10. তাই তো হয়ে গেল। হলো তো? As simple as that. Now if you want to have 12.5, then you can use two pots simultaneously. Again, two pots simultaneously will not give you anything. Sorry, two pots using simultaneously alpha 1 into alpha 2 will still be less than equal to 1. See, how can you get alpha 1 into alpha 2 greater than 1? Because alpha 1 and alpha 2 both are less than equal to 1. right? That's not possible. So to get 12.5, what you can do, you get 0.125 for setting, multiply with 10 inverting. So what you will get, minus 1.25, then multiply again by 10. So you get 12.5. Understood? Mind it, when you are multiplying by any amplifier or inverter, this inversion is there. Okay, inverter will have this, they have this 10 inputs, right? Just like some are inverter integrator, they have this 10 inputs. So in this way, you can simulate this diagram in a similar manner as this. So only this port settings will be different. Right? I will show you the port settings. So this port setting will be 1. This will be 1.25. This will be 0.98. And there will be another port 0.98. I'll leave it to you. I'll leave it to you to obtain this. And say the initial conditions, both initial conditions are 0. Okay. So there will be simulation like this. Now, what about the response? I'll rather move on to the response that you'll get from that response, from that particular port setting. You already know for this particular port setting, what you'll get is an unaddamped response, right? See, let us see. Now, for that, what you need to do is to get the connection diagram. Shall I explain the connection diagram? It's very complicated. It's very difficult to get you through that. Okay, let me explain that. Because otherwise, it will not be very suitable for the class. Okay. So what we have, let me split the screen. It's this, and I don't know whether I can split this screen. Let's check. No, it's not possible. So what we have to do is, split screen will not do. So to get a particular input, say what to get the input, what we have to do, we connect this 10 volt to this port, which is set at 0.98. The output, the input of an integrator. And the output of the integrator connected to the next integrator. It is very difficult to see over here. Can you see this? This, I think this will do. So first, connect your plus 10 volt to this port, which is set at say 0.98, with the output to this integrator input. From the integrator connect to this integrator output will be fed back to this, not directly, obviously. This will go to a particular port on that output, and it back here. The first, this is the second outer loop, and for the inner loop, you get the output from this same connected to a port and get it back. I'm connected to the 10 multiplier because I have the gains 1.25 and 1.96, right? So this will be the overall connection. Then you connect the output of the second integrator to the emitter and see how the response changes. Yes, at input 10 volt. Now we will be observing the step response. Why? Because once I've connected this and turn on the switch, this switch, then what will happen? This input voltage will appear just like a step. So whatever response you are getting will be simply a step response. Let us see how the step response would look like. I have a video for that. So what I will do, I'll only show you the meter portion. Okay. So this is a just follow the analog meter. It has moved up to some value, returned back, and then is moving up again. Just like the response is something like this. Okay, let us start again. Just follow this meter, this meter. As soon as I start it, the response will be something like this. I will try and follow that with a pen. It's growing. Is it? Now it's falling down with a lower peak, slide up, and then settles. Right? So what do you have? First overshoot, first undershoot, and the steady state. Right? So we need to note these values. So steady state is around 4.77 that I've seen. What about the first overshoot and first undershoot? Let us see that. I'd rather stop here. This I think it's very difficult to see show all these things from a laptop or from an online thing, but I've tried my best to give you the idea. This is the first response, the first peak overshoot. What I've done, I've paused the simulation. This is the first peak, 7.59. Then what I've got is the first undershoot. If I draw it here, something like this. This is following the pattern. This value is what I've got 7.59. And this value is 3.70. And finally, the steady state value 4.73. Okay. So these are the different points that we have calculated. Now, I guess you have the idea that if I provide you with this data, 7.59 and 4.73 at the corresponding time, then you can obviously calculate the corresponding damping ratio and omega n, zeta and omega n, right? So as a task, what I'll do, I'll provide you with some data that is not related to this particular simulation, but you have to find out the corresponding zeta and omega n values. So just note down this. Sorry. Peak overshoot value is 6.9 at 2.25 seconds. Then first undershoot 4.2 at 4.6 seconds. This is related to the simulation that is given in your experimental sheet. Second overshoot is 5.4 at 6.5 seconds, and your steady state value is 4.85. So take a screenshot of this, and I will draw the corresponding response and calculate the corresponding zeta and omega values, right? And from that, okay, you obtain the corresponding differential equation and the coefficients. It's like reverse. Okay, and see, I'll give you a hint. This will be the differential equation that is given in your experimental instruction sheet, or near about that, right? So I will take a screenshot. This basically concludes our first experiment, but there's a simple catch that since we are talking about time responses, why should we restrict ourselves to undamped case? So there will be two other cases. Sorry, underdamped case. There will be undamped and critically damped situations. Let us see. Is there somebody wanting to join now? So let us see. Underdamped, let us move to critically damped situations. See how the just we will be concentrating on this, huh? See, it very smoothly goes over to 5. I'll repeat that again. So this is underdamped, sorry. This is your critically damped case. Just observe the response here. So if I draw it corresponding to the it's something like this. And it stays there. Agreed? That's very damped expression. So how that can be achieved? Given that equation that I've shown you for this simulation, you can obviously obtain the critical, and this is undamped. Sorry for the orientation. You can reorient your mobile phone, but for the laptop users, it's very difficult. See, for undamped case, is oscillation, sustained oscillation, like 0, 1, 2. And the frequency of oscillation will be omega n, right? For undamped case. That I think you all know. Undamped, overdamped, underdamped cases, right? I'm not shown the overdamped case, right? So these are the two other situations that you can simulate using this. So what I'll do, I'll now move over to the next experiment. Before that, do you have any query or any doubt regarding this particular experiment? The main objective was to solve a differential equation. What I have seen that the solving a differential equation is nothing like getting the expression of xt, not theoretically, but in a physical manner. We're showing the exact transition of xt or the time response of xt using this analog simulation. And that transition of time response follows the corresponding differential equation. So what we are getting is actually a real-time solution of a differential equation in this analog simulation or analog integration, right? So this was our objective, and you will see that given a differential equation, it practically depicts a second-order system, a second-order differential equation, and by varying the coefficients, we can have underdamped, undamped, or critically damped situations. What I'll ask you that given this equation, you find out the values of, say, this is your f. F. ঠিক আছে for undamped and critically damped case, right? So undamped case is very simple. For this, it should be equal to 0, right? What you have to do is find out the value of f so that the response is critically damped. So this will be part of an assignment. Then you have to solve. Another assignment will be this one. Given this, obtain zeta and omega n and the corresponding differential equation. Because odd and transfer function, because in this case x0 equal to 0, x dot 0 is also equal to 0. They have assumed that they have not put any initial conditions, right? So you have to find out zeta and omega n from this data and the corresponding differential equation, and from that obviously you can obtain the transfer function, right? And this is the data for unit step response for second order system. These are the two assignments from this particular module or particular experiment. ঠিক আছে? Obviously. ঠিক আছে? So this concludes our first part. So in the next experiment, that will be much covered much easily, or very half an hour lagbe hoyto, tao lagbe na. Is a linear system simulator. You know what is a linear system simulator? If you have gone through your instruction sheet, I think you've understood that this is basically a simulator where you can simulate different types of linear systems. And obviously, when I'm talking about linear systems, these are all linear time invariant systems, right? So these are basically, this is a layout. I'll also show you the actual figures. This is a layout where the different systems that we have are an integrator, two time constants. The second time constant has a provision of input multiplier 5. Okay, then we have an amplifier for the feedback path, and we have 3 signal sources. What are the 3 signal sources? A square wave with peak 0 to 2 volt and 20 to 80 hertz variable frequency. We'll be using mainly this square wave for analysis. Then we have a triangular wave and a trigger wave. Trigger wave will be used for triggering the signal externally. So we'll only be using the square wave. So the basic building blocks, if we look at the basic building blocks, there's the error detector. Let me show you the figures. I guess that will be better. This will be the figure. This is connection for the integrator time constant. See, that is not very important. What we have is an error detector here, right? So what is the purpose of this error detector? The error detector purpose is that it has 3 inputs. Look here. 1, reference, feedback, and disturbance. For that, normally we'll use only the reference and the feedback. So what is the purpose of the error detector? That will be much better covered in your next semester. But the main purpose here is to obtain the feedback, to execute the feedback connection. I'll show you. Next is the integrator, obviously. The integrator block is there. This is the integrator block. Right? Then we have a time constant block. So integrator block is of the form K1 by S. There's a gain K, K1 by S, the integrator. The time constant is K2, Ts plus 1. And say this is K3, Ts plus 1. So in the first experiment, what we will do, we'll find out the value of K1, K2, T, and K3 experimental. Okay, so how that can be done? That is to estimate the different elements of the network or the simulator, right? So procedure. So first, run one is open loop response and determination of transfer function. That is K1, K2, K3, T1, T2, assuming that both the time constant have different time constant, the time constant blocks. So first, let us start with the integrator. What we will do, we'll apply a 1 volt peak to peak. But unfortunately, in our experiment, while doing the experiment, you could only apply 0.5 volt peak to peak. And then we will measure the peak to peak output voltage of the integrator block, which will be a triangular wave. And we will calculate the gain based on this formula. Okay. This formula. Let us see how this experiment actually takes place. This is the connection diagram. What I have done, I've connected an input square wave to this. There's someone trying to get in. Interesting. So this is the input. Now I have connected the gain, another line from gain to the input of the integrator. Then output of the integrator is taken to the CRO, right? And this is the common ground of the CRO and the instrument. So let us see now how the behavior is this. So I have put an input to the integrator and taken the output of the integrator and seen in the CRO. So what we will do, we will apply signals of different frequency, 20, 30, 40, 50. And since this is a very flickering, there was very much flickering. So what I have to do, I have to take in video clips of that. So there will be 5-6 seconds video clips. I'll just run them. So this is for 20 hertz. If I stop them, you cannot see. So you have to see in the video only. Okay. So this is the 20 hertz triangular wave that you are getting at the output of the 20 hertz input, output of the integrator. I will show the results, the data. Next, we have changed the frequency to 30 hertz. Okay. Then we will change the frequency to 40 hertz. Always it will be a triangular wave. Then we have changed the frequency to 50 hertz. It's very difficult to capture this. From this, what we obtained, the data that I obtained is given over here. So these are the, assuming the input to be 1 volt, the triangular wave output was this, or the data that you got, and this is the calculated values of the gain K1. The ideal value of gain K1 is 10, but you will get this sort of value. We just check for these values. Okay. So if identified the gain for the integrator, the first part is over. Now you have to identify K2 over the time constant. For that, we'll be applying 100 millivolt peak to peak, the time constant block, and then we'll check for different frequencies, same as previous 20, 50, and 70. We'll measure the output peak to peak values, steady state output peak to peak values, and the corresponding time constants. Right? So the connection diagram will be something like this. See, input This reference is coming over here to the gain. It is coming over to the time constant block. It is multiplied by 5 here. Coming to the time constant block, and output is taken over to the CRO. Very trivial thing. Let us check the open loop time constant. So again, again there will be 3 frequencies. We were talking about 20 hertz, 50 hertz, 70 hertz. Now, what will be the response we are expecting for the time constant block? Since instead of giving a square wave, what are you giving actually? Is a pulse like this. So whenever there's transition like this, you get responses like this for the time constant block, right? As I've already discussed in the first class of time response, then you have to find out gain K1 and say ST1 plus 1, this, sorry, K2, this K2 and T1. The K2 can be found out by calculating the steady state value of this output and the input. K2 steady state output by input. And T can be calculated by the time taken for the response to reach 63.2%. Interesting thing to note here is that we are applying actually a step of this much voltage. Say this is your 0.05 volt. This is minus 0.05 volt. So actually the step voltage is of 0.1 volt step. And your time t equal to 0, we start from this point, and the steady state value is respect to this point. So this is the steady state value, and this is the step size, 0.1 volt. So it will be a step of 0.1 volt. So corresponding to that, you need to calculate from time from this way up to this point, like this. Okay. So in this way, you can calculate the time constant. It's very bad drawing anyway. Like this. Okay. Let us see the data. Sorry. So open loop time constant for different frequencies. I cannot stop. If I stop, it will be like this. So for 50 hertz, 20 hertz, I obtained something like this. I'll show you the give you the values. And we used to calculate the time constant using by stopping this waveform. In this way, if for 50 hertz, see, you can calculate the time constant by measuring the peak to peak values and calculating the time required for this to reach that 63.2% of steady state value, right? So for 50 hertz, you get a response like this. And finally, for 70 hertz, you get a response for this. So in this case, you can clearly calculate the time constant. See, the time constant is gradually the time required for this to reach this value. So you can easily calculate the time constant in this value. So this is the second part of the experiment, and steady state value, see, in all the cases, the steady state value is same as the input. So what about the gain? So gain will be simply a 10 volt, because the scale is something different. See, one scale is 50 millivolt and 0.5 volt. So there's already a 10 multiplier is there in between input and output. So basically input is multiplied by 10. So the output is actually having a gain of 10. You're providing actually 50 millivolt, but it's showing us 0.5 volt in the scale because of the scaling. So scaling factor for the block will be 10, and this is the time constant for different frequencies. Okay, 0.8 millisecond, 1 millisecond, 1 millisecond. From that, you obtain the value of K2 and gain, this K2 gain and the time constant. Next, we have a gain multiplier 5. What is that? If you want to have a higher value of gain for the time constant, you can have this as your input to the time constant block. It is a multiplier of 5. Whatever value you're putting over here will be multiplied by 5. So the gain of the time constant block will be 5 into 10, that is 50. So if you look at the data, I will not show you the results because it's same as previous. If you look at the data, the time constant will be something like this. and the gain will be simply 50. So what we're doing here, we're just studying the open loop response of an integrator circuit. Then we've studied the open loop response of a fast order time constant. And then we've calculated from experimental study the gain and the time constant of the time constant block and the gain of the integrator block, right? Using this linear system simulator. Next, we should move on to the closed loop response. So this is the closed loop configuration. I think in the last class I've discussed about this first order closed loop configuration. So in this GS, we can use either an integrator or this, or what you can use this, right? So these are three combinations that you can have. So this is the first one. So in this case, what will be the closed loop transfer function? The closed loop transfer function will be G by 1 plus G, that is your CS by RS. So calculate that, it will be something like K1 by S, K1 by S plus 1, and we'll be having a gain K. So it will be multiplied by gain K. So what we'll do, we'll change the value of gain K and see how this response changes. See what will happen if you change the value of gain K. And for this transfer function, I think I'll draw it in the drawing board. It will be much better. So case 1, your GS is equal to K1 by S. So your CS by RS, GS by 1 plus GS. Just tell me what will be this value. And this obviously is a K over here. So it will be K1 S plus K1. What we will do, we change the value of gain K. So what will happen? This is the pole location minus K1. As we move on, keep on increasing the value of gain K. This will move in this direction. So what will happen? If in this case, the response is like this, in this case, the response will be much faster, right? Now the response will be given by minus K1T. This is very high, so the time constant will be much less in this case. So as you keep on increasing K, the time constant will tend to reduce. So let us see. See, for the first order integrated block, oh, I have not given the data over here. So actually I have given the data for the time constant block. Let me see the data I have. Oh, I do not have the, sorry, I do not have the data for the first order with integrated block. I think there should be there. So what I'll do, I'll leave it for you. I've given you the hint. What you have to do, right? This K1, you assume K1 equal to 10. And then the value of K, we'll choose this as 5, 7, and 10. 5, 7, and 10. Okay, and obtain corresponding time constant. Okay, and see and draw step responses for K equal to 5, 7, 10. Same paper. একটা গ্রাফে রেখে দেখবে ঠিক আছে expression পাবে, you'll get an expression like this. Okay, so this is another task, but as far as I can remember, I thought I had this data. Okay, you, if I find that data, I'll share it. Okay, if I find the data, I'll share it with you. Okay. Next, what you have is a time constant block as your G. So case 2, the GS is K2 by TS plus 1. So what is your CS by RS? You calculate G by 1 plus GS. So it will be K2 by TS plus 1. Obviously, there will be an gain K over here. KK2 plus KK2. Right? So divided by K. So your upper term will be KK2 by T. S plus 1 plus KK2 by T. So again, if you increase K to different values, you will have this, since T and K2 are fixed, so have this root moving in the real axis. So it will move this direction as K increases. So your response time constant will get reduced. The response will become faster and faster. That is what I have seen here. So K value I have taken for the first order constant block 0.1. The time constant is 0.5. Steady state value I have got 0.48. Steady state is 0.52. How? See, sorry. I think someone is trying to join. So in this case, what is the steady state value? Let's put S equal to 0. We'll get KK2 by T divided by 1 plus KK2 by T. So T will get cancelled out. So it can be written as divided by KK2 1 by, or leave it like this one. So obviously there will be a finite steady state error because of this thing. Okay. So as you keep on increasing K, this error will tend to reduce. Right? Is not equal to 1. See? Ideally, it should be equal to 1 to eliminate the steady state error, but this is not equal to 1. So what you will have is this. For 0.1, the steady state error is like this. When you move again to 0.2, it becomes faster. Steady state value approaches 1 and the error becomes less. That can be shown. So you have to show each of these calculations. How the steady state error can be calculated. For 0.5, T, you have to calculate T, and the steady state error 0.9, and the steady state error will be 0.1. So like this. These are the experimental values. So given the theoretical values that you have with K2 equal to 10, sorry, and T equal to 1 millisecond, if I'm not wrong, you have to calculate or you have to tabulate the theoretical values. This is the experimental values. The theoretical values for all these things. This T, so that is time constant of the closed loop system, steady state value of the closed loop system, and the steady state error. Based on this, because you already know, you have already calculated in the previous step. This is known. The only unknown here is K. So you have the values of K as being shown here 0.1, 0.2, 0.5, and 1. So this is not true. So the value of K 0.1, 0.2, 0.5, and 1.0. So for these values of K, with this known transfer function, calculate. What you should calculate? For the closed loop system, to calculate time constant that will be given by inverse of this steady state value and steady state error. Just you complete the table based on the value of K2 and T that you have derived in a previous step. These are the experimental values. You have to side by side write down your theoretical values. Okay. So this concludes the first order closed loop systems. Now, the next module, the final module, will do a second order closed loop system, and that is achieved by this whatever gain, the integrator, and the time constant. Okay. And I think I have missed out the fact that just like the previous case, all these blocks have a negative value. That is their inverting, right? Just in the previous case. So they're minus K1 by S, minus K3, ST2 plus 1. That is, you are using, note here, you're using a gain 5 here. So you can assume this to be 5 K3 minus 5 K3. So what will be the transfer function? The transfer function for this configuration can be recast. What we'll have now G as K multiplied by K1, K3 into 5. S is there, ST2 plus 1. So calculate CS by RS. It will be coming in this form, omega n square, S square. The only unknown here is K. For different values of K, we will get this expression different. That is, you will get different zeta and omega n. This will be depicted in the experimental result. So I will conclude these two results simultaneously. That's why I've shown you both the things. So first, let's consider the closed loop time constant block. In this case, the nature will be same. The only thing is that the time constant value will change, and the steady state value will obviously change. So this is for gain 0.1. See, having a response like this. So without changing the scale, if we move on to the gain 0.2, it will come. So what I have done, I put an input with 100 millivolt peak to peak. Previously it was 0.1, the gain is now 0.2 with the time constant block and a closed loop. See, there is a obviously improvement in the steady state value. Since they are not in scale, you cannot calculate the error here because the input is in a scale of 0.2 volt and output in a scale of 0.1 volt. So this you cannot just calibrate, you cannot just comment on the steady state error from this. Next, if you move the gain to 0.5, this will be the response. And actually, since it is in output is in 0.1 scale, so we have to get half the value. If you half the value of output, it will be the actual value of output with respect to the input, right? Because the scaling of 2 is there between input and output. Or if you in double the output, sorry, input graph, you get the exact impression with respect to 0.1 volt. Then you can calculate the steady state error. And this is for gain 1. Let's stop it here. See, this is the input part. And this is the output part. So if you, it is almost like, okay, right now, this is from section A. Okay, I'm incorporating. You see, so actually, if you look close, it is like, sorry, almost like the output, almost like two inputs. Since you're using a scale 0.2 is to 0.1, so if you put the input to the same scale of 0.1 volt, what would the input look like? It would double this value. So your input will be this. And then 0.1 scale, what is your output? Almost same. And this is again depicted, or this is again sustained by this fact that the steady state error will reduce for this. And this is the data. No, this is not for the, I guess that was I was showing for the time constant block. See, at a gain of 1, the steady state value is almost same as 1. So error is very, very small. So if you look at this figure now, if you multiply it by that factor of 2, then you will get almost same value as input and output. Right? So this is how the time constant will change. Time constant will also change. It will be becoming much and much faster as you increasing the gain. Now you see the final expression, that is a closed loop. For that, with the second order closed loop with integrator, we use 3 gains, 5, 7, and 10. And you will see you will get an underdamped response with zeta values calculated as this. And corresponding omega n values will be like this. So I have given you the experimental value and theoretical value, but it will be your task to find out the theoretical values. Okay. I've already given you these things. You have to cross-check these values, right? I'll provide you with the PDF. No need to take the screenshot. So for gain 5, the second order response, say, is basically second order response, right? So you'll have this underdamped response for gain 5. For gain 7, what will happen? The zeta will change and omega will also change. It's very difficult to appreciate the change from this. In this case, see the scales are same, 0.2, 0.2. So the output resistor is very, very small, almost 0. Okay, this will be discussed in the latter part in the control theory class. These are called the type 1 systems. But there's an integrator in the forward path. That's why the resistor error will be 0. And for the gain 10, this is the response. So either of the cases is very difficult to find out the actual response. So what we'll do, we'll look at the figure, this table. As we have mentioned that you change the value of k, zeta and omega n will both change. And that is what is happening. See, for gain k, we have calculated zeta from what? From MP, TR, TP, and TS, from this data. We have calculated this data from the CRO graph. From that, we've calculated zeta and omega n. And this zeta and omega n can be calculated based on the theoretical result, because all these values, K1, K2, and 5, K3, this is T1S, T2S plus 1. These are all known. They've already calculated this K1, K2, K3, and T1, T2 in the first part of the experiment. So from that, you can obviously obtain the transfer function, closed loop transfer function for different values of gain K. From that, you can theoretically calculate these values. So it will be your task to calculate these values and validate the table. Individual values you have to calculate and validate. This experimental data, you have to think this is given. So you have to calculate this entire part. Okay, from this data and the theoretical values that you already calculated. Or you can take the nominal value. K1, K2, K3 equal to 10, T1 to 1 millisecond, bus. Right? So this concludes the linear system simulator, where we're using the simple building blocks like an integrator and all. fundamental building blocks like this integrator, 2 time constant, and a variable gain. What you can simulate? We can simulate first order system, second order system, and as you're changing gain k for the first order system, what is changing? We're changing the time constant. Second order system, we're changing zeta and omega. And there's obviously provision for third order system using integrator, time constant, right? So that is beyond the purview of this syllabus of this lab or for you, because you're not very much acquainted with third order system. So this is up to first and second order. There may be another second order system that will comprise of the 2 time constant blocks. That is, if you connect this, follow?
হ্যাঁ স্যার আমাদের অ্যাসাইনমেন্ট গুলোর টাইম কদিন, মানে কয়দিনের মধ্যে সাবমিট করতে হবে?
কোনো টাইম নেই, তোমরা যত তাড়াতাড়ি পারো, এখন তো টাকটা শুনছো, ভিডিওটা দিয়ে দেবো, যদি কোনো ডাউট থাকে তোমরা এখনই করে রাখো, ঠিক আছে?
আচ্ছা স্যার।
কোনো ডেডলাইন নেই, you do not have to submit that. You get it ready and a neat করে you just write down on a white paper or lab sheet or whatever you have, A4 paper, mentioning your name and roll number and section. Keep it ready with you, all the calculations. Okay, if it is required, then I'll ask for it and I'll give you 2 days to submit. So it's better, since you're not having an exam right now, better in next 2 days you complete these assignments, right? So that is, এটা তো টাটকা শুনছো, এটা তোমার মাথায় থাকবে, ফলে সুবিধা হবে, যতটুকু বুঝেছো কাজে লাগিয়ে ফেলো। আর যেগুলো বললাম থিওরি পার্টটা আমি তোমাদের নেক্সট সিগন্যাল সিস্টেমস ক্লাসে ডিসকাস করবো, but that is Thursdays too far. And you নিজেরা চেষ্টা করো, if you have any doubt, we'll discuss in the signal systems class, right? Okay, because it's all part of signal systems, right? So feel free to ask me in the signal systems class if you have any doubt. In between যতটা পারবে at least jot down করে রাখো কি কি করতে হবে, সেটা ক্লিয়ার হয়ে যাবে, ঠিক আছে? Any notification regarding your viva lab experiment? I think lab exam?
স্যার 8 তারিখ।
8th May?
Yes sir.
Okay, কোন টাইম দেওয়া হয়েছে?
স্যার 12:30।
ওকে ওকে ওকে। তুমি কে বলছো, কোন সেকশন থেকে?
স্যার এ সেকশন থেকে।
Okay, I think it's the same for A and B section, right?
Yes sir.
Okay okay. So I think I'll stop here. If you have any doubt, you'll feel free to ask. See, first of all, I'll admit that it's very difficult to explain the laboratory setup and laboratory experiment via this online mode. So I've tried my best to put up the videos and things like this, and still I'm not very convinced with this presentation, but you have to go with it. So it is absolutely impossible to reach the university now. So whatever you are having, I can devote more time if you want, but that is what we have. Cannot go beyond this, right? So I think I'll give you the videos. I'll give you the individual videos and the video of this particular lecture. You just go through them, right? And if you have any doubt or confusion, feel free to ask me. You can ask me over WhatsApp, or you can mail me, or you can note down your questions. We will discuss in the signal systems class, right? Next Thursday. Okay. So
Okay, sir.
is it all? Do you have any queries, really? As of now? I think I know it's very difficult. I have put down so many information right now. It's very difficult for you to appreciate everything. So take your time. Okay, I'll discuss about this on next signal systems class on next Thursday, right? Okay.